We now look at a new method of proof known as induction. Now, in natural science, deduction and induction are presented as alternative modes of thought. Deduction is used to infer a conclusion from general principles using the laws of logical reasoning. Induction is used to enunciate a general principle after observing it to hold in a large number of specific instances. However, mathematical induction is not inductive, it is actually deductive. Once a statement is proved via induction, a theorem is known just as certainly as if it were proved by any other mathematical method. Now, inductive reasoning is used in mathematics, but only to make a conjecture, not to actually prove it. For example, you may notice a pattern that seems too unlikely to occur by random chance. So it is reasonable to conjecture that the pattern holds true in general. However, this is not an actual proof of the conjecture. The idea behind the proof by induction, or simply known as mathematical induction, is to ask, is there something about the form of the pattern in one case to ensure the pattern will be true for the subsequent case? So here is the principle of mathematical induction. We let P of n be a property that is defined for integers n, and let a be a fixed integer. Suppose the following two statements are true. P of a is true, and for every integer k greater than or equal to a, if P of k is true, then P of k plus 1 is true. Then the statement for every integer n greater than or equal to a, P of n, is a true statement. So now the actual method of proof by mathematical induction. Consider a statement of the form for every integer n greater than or equal to a property P of n is true. To prove such a statement, we must perform the following two steps. The first step is known as the basis step, and that is to show that P of a is true. That is, show the property is true for the first possible value of n. The second step is called the inductive step, and that is to show that for every integer k greater than a, if P of k is true, then P of k plus 1 is true. Right? And then here's how the proof follows, right? We've already shown it's true for the first case. If we can then show that if it's true for one case, it's true for the next case, then it means it would be true for a plus 1. But then that would mean it has to be true for a plus 2. But that means it has to be true for a plus 3. But that means it has to be true for a plus 4, so on and so forth. So this shows that it now must be true for every case larger than or equal to a. So we're now going to go ahead and prove that for every integer n greater than or equal to 1, the summation from k equals 1 to n of n is n times n plus 1 over 2. What this is saying is that the sum of the first n positive integers is the average of n and n plus 1. So for the proof, we start with the basis step. That is, we have to show that it is true for n equal to 1. So for n equals to 1, we have 1 times 1 plus 1 over 2. Well, that is 1 times 2 over 2, which is 2 over 2, and that's just 1. Well, the sum of 1 is just 1. So 1 equals 1, and we're done. Now for the inductive step. So suppose that for some integer k greater than or equal to 1, the sum from I equals 1 to k of I is k times k plus 1 all over 2. So we're assuming that this is true for every integer, or for some integer k greater than or equal to 1. What we want to show is that it's true for the second, or for the next integer. That is, we want to show that the sum from I equals 1 to k plus 1 of I is k plus 1, right, that's k, times k plus 1, which is k plus 2, all over 2. All right, so if it's true for k, then the sum from I equals 1 to k plus 1 of I would be the sum from I equals 1 to k of I, then plus k plus 1. So from here to here, all we did was we pulled out the final term, which we saw in the last video. But we know by assumption that this has to be k times k plus 1 over 2. Well, now we have to add the fractions together, so common denominator is 2. So it'll be k squared plus k, then plus 2k plus 2 all over 2. This becomes k squared plus 3k plus 2 all over 2. And then from algebra, we can see that this factors to k plus 1 times k plus 2 all over 2. And typically, we would stop there. That would be the end of the proof. However, we can thus conclude from induction that for all integers n greater than or equal to 1, the summation from k equals 1 to n of k is equal to n times n plus 1 all over 2. Now, we're going to use this property to compute some sums. So, let's compute 2 plus 4 plus 6 plus 8, blah, 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 plus 500. So 2 plus 4 plus 6 plus 200, plus 500. Well, these are all even, so we can factor out a 2, and we're left with 1 plus 2 plus 3, blah, 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 plus 250. Well, this is the sum of the first 250 positive integers. So by the previous theorem, this will be 2 times 250 times 251 divided by 2, which simply is 250 times 251, and that product is 62,750. Which means that this sum is 62,750. Okay, well, what about this sum? So 5 plus 6 plus 7 plus 8 plus 50. Well, notice that the only thing we're missing from the theorem would be the first 4 positive integers. So let's add them in. I'm going to do that in a different color, actually. All right, so I've now added them in. So now I can just keep going. 5, 6, 7, 8. However, I'm not allowed to just add things in. It changes the value. So if I add 0, though, it doesn't. So since I added 1 plus 2 plus 3 plus 4 in, I'd have to immediately subtract 1 plus 2 plus 3 plus 4. Now I've added 0, and I have not changed the original sum. So this first is the sum of the first 50 positive integers. So that is 50 plus 51 all over 2. Then it has to be minus 1 plus 2 is 3, plus 3 is 6, plus 4 is 10. I'm sorry, this should be a times, not a plus. So this is 2550 over 2 minus 10. 2550 over 2 is 1275. And so the sum is 1265. So we're now going to use induction to prove an inequality. So for each integer n greater than or equal to 0, I'm sorry, we're proving a divisibility in this one, not inequality. So for each integer n greater than or equal to 0, 2 to the 2n minus 1 is divisible by 3. So the base step is to show that it is true for n equals 0. So for n equals 0, we have 2 to the 2n minus 1, which is 2 to the 0 minus 1, which is 0. Now, 3 divides 0. So the base case has been proven. Remember, any integer divides 0. So now the inductive step is suppose that for some integer k greater than or equal to 0, 3 divides 2 to the 2k minus 1. Note that this means that there must be some integer q such that 2 to the 2k minus 1 is equal to 3q. We want to show that 3 divides the next case. So 3 divides 2 to the 2 times k plus 1, which is 2 to the 2k plus 2 minus 1. Or that 2 to the 2k plus 2 minus 1 equals 3 times r for some integer r. All right, so 2 to the 2 times k plus 1 minus 1 is 2 to the 2k plus 2 minus 1. Using properties of exponents here, we can write this as 2 to the 2k times 2 squared. 2 squared is 4, so this becomes 4 times 2 to the 2k, then minus 1. But 4 can be written as 3 plus 1. And now if we distribute this 2 to the 2k in, we'll get 3 times 2 to the 2k plus 2 to the 2k minus 1. We can group this together. And since we've already said that this is divisible by 3, it has to be 3 times 2 to the 2k plus 3 times q. Now we can factor out a 3, and we have 3 times 2 to the 2k plus q. But this term is an integer. So we have just written 2 to the 2k plus 2 minus 1 as 3 times some integer r. So 3 divides 2 to the 2k plus 2 minus 1, and we can thus conclude by induction that for all integers n greater than or equal to 0, 3 divides 2 to the 2n minus 1. And so the proof is complete. Now we will use induction to prove an inequality. We will prove that for every integer n greater than or equal to 3, 2n plus 1 is less than 2 to the n. So we have to start with the base case. So the base step is to show that it's true for n equals 3. Well, for n equals 3, 2 times 3 plus 1 is just 7, and 2 cubed is 8. Now, 7 is definitely less than 8, and so we have 2 times 3 plus 1 is less than 2 cubed, so the base case has been proven true. Now the inductive step. Suppose that for some integer k greater than or equal to 3, 2k plus 1 is less than 2 to the k. We want to show that this must be true for the next case, that is, 2 times k plus 1 is less than 2 to the k plus 1. Now, 2 times k plus 1 is 2k plus 2 plus 1, which we can write as 2k plus 1 quantity plus 2. But by our inductive hypothesis, this term right here, this 2k plus 1, is less than 2k. So this whole thing is now less than 2 to the k plus 2. Now, since k is larger than 3, 2 has to be less than 2 to the k. This means that 2 to the k plus 2 is less than 2 to the k plus 2 to the k, which is 2 times 2 to the k, which is 2 to the k plus 1. So we have just shown that 2 times k plus 1 was less than 2 to the k plus 2, but 2 to the k plus 2 is less than 2 to the k plus 1. So by transitivity, 2 times k plus 1 is less than 2 to the k plus 1, and we can thus conclude that for all integers n greater than or equal to 3, 2n plus 1 is less than 2n. And the proof is complete. And that concludes our study of induction.